This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. My guest is the CTO and co-founder at Groundcover, which provides full-stack observability for Kubernetes. He was previously the chief architect at the healthcare security company CyberMDX and spent 8 years in the cybersecurity division of the Israeli Prime Minister's office. He holds degrees in electrical engineering, physics, and biomedical engineering. First, I'd like to ask you to pronounce your name and if there's anything you'd like to add to your bio.
Hey, so it's Yeckezkel Rabinovich, but you can call me Chez. It will be easier. Yeah, mainly worked around Linux, embedded software, and distributed systems in the last 10 years or so.
Great. This episode is going to be at the intersection of three technologies: observability, eBPF, and Kubernetes. I'm not going to go into too much depth on either one of these, so I'm going to list three episodes here that covered it in more detail. Episode 455, Jamie Rydiesel on software telemetry. Episode 446, Nigel Poulton on Kubernetes fundamentals, and episode 445, Thomas Graf on eBPF. Let's start with observability. Jez, what is observability?
So it's common to think about observability in three pillars of data. One is logging, the text messages we are creating from our applications. The other one is metrics, which are basically counters and gauges that our application of creating. You can think about that as the speed of a car, right? That's a gauge, right? The amount of fuel you left in your car. And the third one is tracing, which are samples of data that represent interactions between two services. So if you're calling an HTTP request, that will be a trace or a span, which is part of a trace. And observability is the ability to query all those three in a very meaningful way of troubleshoot or understanding the state of application. It could be for security, it could be for performance investigations, basically everything that developers are interested in.
From my experience, observability can make a huge difference to sort of the quality of life of the developer trying to get to the bottom of some problem. Can you give an example of a system that didn't have good observability, that was a struggle to work with, and contrast that with something that had sort of full observability and how that accelerated the debugging or the investigation?
Oh, yeah. Actually, I have a good example of I think that was the trigger for me to start Groundcover. So we had a problem with our platform where customers experienced data loss, and we had some complex pipeline of data. So, 30 microservices all talking to each other with message queues and Redis and API calls and everything you can think of from a modern application. And so, where do you start, right? We got this lead that our customers saying, we're missing data, but where do you start? At that time, we had a lot of logs, but we paid a lot for them. But, you can't really read for, 20 or 30 million logs line and understand what's going on. So we've decided to instrument our application with a lot of counters that will represent the pipeline of the system. So it took us somewhere around 2 months to instrument. We had somewhere around 1 million counters. And then we can finally detected where the leakage is and start solving it. But this process was a nightmare, right? So we walked 2 months just to see where the problem is. On the other hand, when we started Groundcover, we knew that we had to set as an example to how you observe and monitor production. So we built our entire stack from day one to have performance monitors and meaningful logs and traces that will help us troubleshoot and investigate any performance issue. So, it feels like the difference is like, using a paper as a map or a navigation app. That's the difference for me, something guided, not, you don't need to search for, just see answers.
Yeah, it's a major difference. Let's move on to eBPF. eBPF is a technology that's used perhaps for many different purposes. We're going to talk about observability, but let's just talk a little bit about the technology at first. So what is eBPF?
eBPF is technology, as you said, that allow you to dynamically change and adapt the Linux kernel. So a lot of people can, first thing they can say, a lot of people that work with Linux can say, okay, was easy before, you could write a kernel module to extend the kernel. But the reality is that writing a kernel module to extend the kernel is a very complicated task. And also it could be very harmful if you make a mistake. eBPF is a technology that allows you to extend the kernel with a very safe way. Safe in two important aspects. One is from performance aspect. So the eBPF engine that run your program, it guarantee that you program are running very efficiently and they cannot harm the application itself. And the second one is you're running in a read-only mode. Of course, there are different eBPF programs, and I'm not sure we should get into that. But in terms of observability, you can run programs with read-only mode that can guarantee by the kernel to not change the state of the application. Those two allow you to develop your modules very efficient and very fast.
So some people say eBPF is to the kernel like JavaScript is for the browser. Do you feel that's a good analogy, or how would you phrase that?
Yeah, I've heard that many times before. I think it's a great analogy because when you write JavaScript, you don't really worry about are you going to run on a Intel machine, or it's going to be a Mac, or it's the amount of resources you're going to have. You're running in a sandbox and you get guaranteed by the browser that your code going to run. And I think that's the magic of eBPF. You can run your program without being worried about affecting the Linux itself or the hardware itself. And this is something very, very powerful in terms of speed of development, because developing for kernel today is almost slow as developing hardware. So I do really agree with this analogy with JavaScript, which is basically speed up web development. So I think that's for the kernel. Yeah, definitely.
So that's interesting. Which languages can you write eBPF? And are you saying that whatever language you use, it compiles down to a bytecode that works on any architecture? Or do you have to compile it again for x86 and ARM? And I guess which languages do you prefer to use for eBPF?
So as you said, eBPF is a bytecode itself. So that's the VM running your instructions and translated to the proper instruction set. So you don't need to worry about running on x86 or that's the kernel will translate it. And it's really, I know some people write in different languages, high-level languages that compile to eBPF, but I think the majority of software is written in C, because that will be the easiest way to write an eBPF program. And don't get me wrong, it's a hard process learning how to code C code that can translate into eBPF. It's because the eBPF verifier is very picky in choosing what programs you should run. So you kind of need to learn how to work with the compiler to verify your programs and that they're safe to run and very efficient. So most people write in C, which translate into eBPF bytecode and run with this VM with abstraction of the hardware itself.
So how about the eBPF verifier? Does that run when you compile the code? Does that run when it's loaded into the kernel? And can you give an example where you did have to kind of fight with the verifier? What did you have to do to your code to appease the verifier or to make it load your code?
So the verifier runs when you try to load the program. And it depends on the kernel version, because when kernel get more sophisticated with eBPF, the verifier get smarter and smarter and allow you to do more sophisticated things. Because again, the purpose of the verifier is to make sure your program is safe. So in terms of things we had to do, you don't want to know. It's a hassle. It could be a hassle. Even sometimes, copying data from A to B, and make sure you don't have out of bounds copy. You really need to work in terms of making the verifier happy. Some people at Groundcover call it, to know how to dance with the verifier. There are a lot of examples, and every eBPF programmer probably, has this kind of stories every day. It's a great technology, but it's still, in order to make it safe and to make sure, you can process so much data in a safe manner, the verifier is picky. You need to know how to please it.
So a big part of eBPF are hooks. And I read about you can hook system calls, function entry and exit, kernel trace points, network events. Can you give kind of just an overview of the different types of hooks and indicate maybe a little bit what they're used for?
There are two major hooks that you can use, and they're separated by the space they are. So if you want to trace kernel functions, you'll use kprobes. And if you need some kind of user space information, you'll use uprobes. So why would you care? So kprobes are a lot cheaper because you're already running in kernel space. So you don't need to worry about context switch and interrupting your application. So you'll probably want, if your information that you're after can be retrieved from kernel, you probably want to do that. And there are a lot of books about that. I think Brandon Gregg wrote a lot about that. But sometimes your information could not be retrieved from kprobes. I'll give you a simple example. Imagine you want to trace SSL data. The SSL for most runtimes user space encryption, and you have to get the information from uprobes. So you'll use uprobes for the libSSL lib. So of course it will cost you a little bit more because it's a user space application, and now you kind of have to interrupt, but it's the only way to get it. So you need to use it wisely.
How about network events? I think eBPF originally stood for Extended Berkeley Packet Filter, although I read on the eBPF homepage, they're trying to kind of drop that acronym and just call it eBPF itself. But I imagine network events are still a primary domain for eBPF. I read about dropping packets. It wasn't immediately obvious to me why you'd want to drop packets at the eBPF level. Can you give an example of filtering, which I guess is the original use?
Yeah, sure. So imagine you're writing a firewall and you want to do it high speed and you want to enforce policies. For instance, you cannot access an external IP to this subnet. So eBPF can do that for specific programs. So you can load specific programs that can also drop packets. So I think the majority of this use case is probably security and high throughput processing. With Groundcover, we do not use these kind of programs because we don't want to change flow of information. The opposite, actually. We're trying to extract as much information as we can without interfering and to guarantee that. So that's the common use case of dropping packets. You can also use in the last, I think, releases, you can also do signaling from the kernel. That's also really powerful from security perspective. You can signal the process and even, sending termination signals to processes if they're doing something wrong. So I think security is a major use case for these kind of programs. I'm sure Thomas with the episode probably talk a lot about that and Cilium project that uses all those kind of programs.
So to be clear, with the uprobes, even if you're in a read-only mode, that is a lot of access in the sense you can look at the memory of any running user process. That's pretty alien to me as an application developer. I just don't think about being able to look inside processes. But that's true. So I guess you really want to make sure no one has loaded a eBPF program that you don't know about.
Yeah, so you need to give right permissions. In order to load eBPF programs, you need to have specific capabilities from the Linux perspective. Probably need an elevated user or a privileged container if you're running on a Kubernetes environment. So yes, definitely, it's amazing technology when you get a lot of information, you need to use it wisely. So you need to make sure when you're running these kind of programs, you need to make sure you understand what they're doing and who is using it and why.
So maybe just two more about eBPF, and then we'll move on to Kubernetes and then on to observability with Kubernetes and Groundcover. So there are eBPF helper functions and there's eBPF maps. I'm just wondering, do those two relate? And particularly, how do eBPF maps work? It sounds, again, unusual to an application developer. So it'd be interesting to hear about that.
So in order to write programs, right, we need to have some kind of data structures. We're actually pretty used to them as application developers. So for instance, list or an array or map. Those are kind of data structures that we all familiar and love and need in order to use our application. And so those are the same for eBPF, because eBPF verifier need to make sure we do not access arbitrary memory. The data structures that eBPF programs need are created by the kernel. So you work with functions that are giving you the equivalent opportunity, the equivalent features of data structures that you have on your application. So map, array, TTL or LRU cache, all of those data structures exist in the eBPF ecosystem. And we need them in order to write efficient and meaningful applications.
So I guess one of the things the verifier is probably doing is limiting the amount of CPU time that an eBPF program can have. And you're talking about limiting memory access too. What are those limits? Are they in milliseconds, or how does that get measured?
So it's configurable, but now I think milliseconds are out of the healthy zones when you write eBPF programs. We're usually talking about hundreds of nanoseconds. That will be a good direction. And it also changes with the kernel version itself. So the community is trying to increase the complexity of eBPF programs because of the demand. So a lot of products are trying to push down some of their application into eBPF. So they're also trying to increase the complexity and the instructions that eBPF program can run. But it will be around microseconds, not milliseconds.
Wow, that's interesting. Let's move on to Kubernetes. Kubernetes is a huge topic, and we are only going to touch on a few elements to sort of set the scene for the rest of the episode. But let's start with, what is Kubernetes?
So that's a good question, because a lot of people describe it differently. So some will tell you it's an orchestration for containers. And some, and me, I personally think it's more than that. It's a modern operating systems, because you have all the storage, network, scheduling, all the primitives that we used to know from other operating systems, but it's very native to containers and to cloud. So to me, it's a cloud native operating system that allow you to run and orchestrate containers and manage the resources that each needs.
I like the term cloud native operating system. When I first moved into cloud development, I did feel that all of the individual systems reflected operating system primitives that we had on a single machine. And so I think that's a good way to think about it. How about the relationship between Kubernetes and microservices? If you're using Kubernetes, does that imply you're using microservices, or is Kubernetes broader than that?
Not necessarily, but if you're using Kubernetes, using microservices will become much easier, because microservices require some kind of orchestration. So for instance, network, you need to be able to reach each and every microservice, need to find the resources that it needs from others. Kubernetes will take care of that. What do you do when you upgrade? How do you upgrade? What are your upgrade strategy? Kubernetes have primitives for that, to maintain the relationship between microservices. So you don't have to use microservices when you're using Kubernetes, but it will be easier, and Kubernetes will probably be a pretty good decision if you are heavily using microservices.
So I think a big part of Kubernetes is deployment, in the sense of running the containers or systems that you want in the configuration that you want. Is that true, that it's mostly about deployment, or once your application or your backend is up and running, what role does Kubernetes play sort of moment to moment?
So to me, the promise of Kubernetes is the reconciliation loop. So as developers, we know that things can go wrong. Something can shut down. Some machines will break. Some storage will be corrupted. And one of the fundamentals of Kubernetes is the reconciliation loop. So basically what it means is we have the actual state and the desired state. And what Kubernetes promises you is to do everything it can to bring the current state to the desired state. So if a process crashed because, someone, network outage, Kubernetes will detect that and recreate it and make sure it's healthy on another node or another network. And to me, that's what's so great with Kubernetes. It doesn't really say, bad things won't happen to your production. It's all about making it high availability. It's more like things going to happen, but we are going to do everything we can in order to fulfill the promise that you ask for us.
So in Kubernetes, there's sort of hierarchy between these elements: containers, pods, nodes, and clusters. Can you talk about these and mention which of these does the eBPF program operate on, and just sort of how these different levels relate to observability?
Clusters are an abstract word of, a group of resources, a group of nodes, if you want. Nodes are the machines. So that's the physical representation of all your compute. So we're taking nodes and now we need to schedule workloads. So deployments or replica sets or wherever you're using with Kubernetes ecosystem. So now Kubernetes, the control plane, has those resources, the nodes, and the desired state, which will manifest with 10 pods that will hold, 2 containers each. And it will start to allocate resources. So the containers will run on those nodes. And if one node will crash, it will transfer it to another. And when you scale up your cluster, more nodes will be spinning up and more pods will scale up. So when you monitor this kind of environments, you want to separate between those two planes. One is the infrastructure. So we want to make sure all of the nodes are healthy, not overbooked with high memory or high CPU usage. The network is fine. And a lot of those things can be easily achieved by eBPF, right? We just talked about eBPF is being part of the kernel. So each node has its own kernel, and therefore the eBPF program will cover that. And on top of those, you'll have the application itself. So even if our infrastructure is fine and your application is, returning some broken APIs, serving broken APIs to customers, that's also not a good thing. But it's important to separate between those two planes because usually it's different people responsible for those different planes. You have the platform team or the infra team or whoever is responsible for the infrastructure, and you have the R&D or the team that actually create the application that's responsible for those. So it's really important to have the ability to separate between those two. And actually, when you think about it, eBPF is also helping with that because on each and every event, you can correlate it to who is responsible for it. So you can detect if it's a pod that's triggering this API or it's a node. Is it a kernel thing or is it a user space thing? So you want to have both, and you want to be able to separate that in order to find the right people to help with this incident.
I'm going to ask about Kubernetes events in a little bit. But first, Docker seems like the most predominant container system, but I read that Kubernetes is not necessarily bound to using Docker. Can you say from your experience what container systems you have seen, and do they play a challenge for observability?
Yeah, there are a lot of new orchestrated containerization environments. I can't really keep up. But at the end of the day, Kubernetes, it's not about how do you containerize it. It's about using containers. So from the Kubernetes perspective, it's like a plug and play, right? If Kubernetes, we talked before about scheduling pods, right? So eventually it's running a container, which has an image or manifest and make it schedule in the Linux ecosystem. And from there, it's the containerized layer to how it will resolve in the Linux primitives. So from Kubernetes perspective, it doesn't really matter what containerized platform do you use.
I did see that Kubernetes allows you to plug in different systems depending on your needs. It sounds very configurable. How about networking? I think networking is a big aspect of Kubernetes. I imagine there's communication going on between pods, but then also between nodes, and then also with the outside world. Can you talk just a little bit about Kubernetes? If I'm setting up, say, a new system, what are the different network paths that I might care about?
you have a few objectives that you want to achieve with networking in Kubernetes. First, you want to being able to discover your other microservices. And remember that Kubernetes is a flexible system. So one service can hold 100 pods behind it for this moment, and tomorrow it's going to have 400. So you need to keep track on those IPs. How can you reach the microservice that you're after? And this process can be really expensive in terms of compute and finding the right IPs and maintain it. So eBPF is obviously one of the solutions for that. And Cilium is a great project that try to push down all these translations and rewiring of packets to eBPF to do it very optimized. That's one challenge with Kubernetes. The other one is, how do you expose some services to the external world? So you want to wire it with cloud providers. You want to connect it to NLBs or ALBs, and you wanted everything to be natively and to be as Kubernetes as you can, even though it's interacting with actually cloud provider, which are opinionated. So that's another thing that cloud providers are doing. They're using the pluggable ecosystem to join resources between Kubernetes to the cloud. So you can provision an ingress controller that will eventually wire to an AWS NLB or the equivalent of GCP or Azure, and it will work out of the box with the Kubernetes native way. So that's a pretty big one, because in the past you had to rewire your application in a proprietary way. But today, because Kubernetes is becoming de facto standard, cloud providers doing it for you and making it Kubernetes native as possible.
Let's talk about APM in the context of Kubernetes. So I think that's application performance monitoring. Can you give us a little overview of that?
APM is a general name that represents, taking all the three pieces of observability and tie it together to make some meaningful insights from it. Specifically, APM is some related to traces specifically, because this pillar is a bit more hard to get, right? Because you need to either instrument your application, which could take a lot of time, or use some kind of eBPF sensor, which just recently became available. So APM is a general name for gathering traces and tie them with metrics and logs.
When you say traces, I think of a stack trace, which is a single program, function calling function calling function. Is that what you mean? Or is there sort of a broader type of trace that would involve multiple programs?
It's the extension of that. So you're right. Stack trace, it used to be, the chain of events that happens, A equal to B equal to C. But then we started using microservices. So now A and B are no longer using the same process. So it's really hard to get a stack trace for a few microservices talking to each other. So each and every call is called a span. And the chain of spans are called a trace, which trace this business unit from A to Z and can investigate it to see where the bottleneck is, where do you get error from, and everything you need to in order to investigate this incident.
So I guess the key with APM is that there are applications and user applications or backend applications as opposed to the system itself. When you think of observability with Kubernetes, how does that divide in terms of what technologies are focused on the system versus the applications? Or is it basically the same technology?
So we do have those two planes we talked about earlier about, the infrastructure plane, which are agnostic to the applications that are running on top of it. So you want to make sure the infrastructure is healthy, you have enough resources in order to fulfill all the requests that you get as, to deploy those kind of microservices, to doing an update and so on. So this is one plane that you want to monitor. And obviously, if that's broken, everything else is going to be broken. But still, if that's healthy and all the nodes are healthy, that doesn't mean that your application is running smoothly. There could be a network errors between applications. There could be, wrong configuration, different passwords, could be a lot of things. So the other plane is the application itself. And that's harder to monitor, because in order to do that, you need either instrument each and every application, and not all of them you wrote the code, and there are third parties that you're not aware of, and so on. And so that's really hard. Or you can use eBPF as a sensor, which basically automatically detect all those traces and all those spans and applications and get all these data automatically, regardless if you instrumented the application.
How about the term service level objectives? Is that basically the amount of uptime that your services have, or could there be other objectives?
Yeah, so each and every platform will define what is their SLOs. So what do you promise to your end users or customers? What are the standards that you are achieving when serving their applications? Usually we tend to see a latency promise. So, P95 of all requests will be under 200 milliseconds, for instance. That's a really common metrics. And of course, I think the golden signal will be error rate. So what will be the error rate that we can guarantee to you as an end user or customer that our platform will provide? And to measure those, that's not an easy task. Like, it sounds simple, but in order to measure those kind of signals, and in order to do that without being involved in each and every process, you either need to use some kind of eBPF sensors, or you need to have a dedicated team that will make sure that everything is implemented, all the metrics are instrumented, and check that there are no drift. Because sometimes we think we're done, and then a new developer add a new API, and we forgot about that. So now it's not just we broke our SLO, we don't even know that. So that's not a nice situation to be in.
You mentioned P95. Can you explain what that is and why you use metrics like that as opposed to, say, average, which maybe is a simpler way to put it?
Yeah, so P95 is a unit of how do we measure distribution. So this will be the latency that 95% of our application, of our APIs will be less than this latency. And why it's important, and we're seeing actually a phenomena where companies are focusing around P99 or P99.9 because it really depends on your SLO. So think if you're a bank and if you have P99 of 100 milliseconds, but then you have this anomaly that takes 30 seconds, 1 out of a million, you won't notice it on the average, right? It wouldn't change the average at all because it's 1 out of a million. But it could break a trade for a timeout. So those numbers could be very crucial. It depends on your industry and your specific needs, but we're seeing more and more, especially in the gaming industry, especially in the ad tech and fintech, that those anomalies, those 1 out of 1,000 are matters. And for those, you need to measure P99 and P95 and not only average.
That makes sense that there's going to be a few exceptional events that are much slower than the rest. How about Kubernetes events? We mentioned that early on. Can you give specific examples of a Kubernetes events? Are these related at all to eBPF hooks or events, or is it just a different topic?
It's a different type of events. Kubernetes is trying to expose some of its state in order to help us developers troubleshoot. So it generates events, normal events, warning events, just to give you a clue of what it's doing and where the problems are. So those are actually really important because you can find events such as image pull backoff, for instance. So it means Kubernetes is trying to fetch this container image and can't find it. That will probably indicate on a serious problem. It could also have events such as crash loopback. So it means your container crashing and you probably need to check what's going on. So those events could be meaningful, but they could also create a lot of noise. It's really important to know that Kubernetes generates a lot of events all the time because that's how it works. So it could be really important, but you really need to understand and digest and dissect what are the key events that you want to track.
You mentioned pulling an image. I did read about deployment changes such as images, config, dependencies. And I didn't really think about that in the domain of observability. But I imagine with microservices, if you have a large system, there could be many different dependencies. And which ones were running when something bad happened is non-trivial to figure out. Can you say a little bit more about that? How are we tracking what is actually running at a specific point in time.
You're definitely right. And especially when those days companies trying to push more and more version each day. So it used to be one version a week. So you could basically estimate what was it at that time. But today we're seeing companies pushing releases like 10 times a day, maybe 20 times a day. So what we do at Groundcover, because we generate all those data, we tag it with those specific labels. Each and every information, each and every trace or log or metric, you want to tag with the right container image or hash in order to make the troubleshoot and the investigation much more meaningful. Because in that way, you can see, oh, those broken APIs started with this commit. It wasn't before, and I can see it because it's all tagged. So it's really important to achieve that. You can obviously do that with adding labels to your instrumentation. So you can add a little bit of annotations on your deployments or in your code. So it's really important to maintain that in order to get a clear sense of what was the version, what was the exact state of the code at that level.
How about the Kubernetes API itself? Is this giving us information about all of these different things, or is the API specific to the cluster, or just how does that work?
Those are, to me, are the most important things, because if your control plane, if your, the infrastructure doesn't really work, if your node getting errors from the control plane, the Kubernetes control plane, that's really bad. And that could be a sign that the system is going down completely. So there are those APIs which are really hard to get because they're not instrumented. The kubelet is not instrumented. So it's really hard to detect. You can be detected with logs if you are monitoring your control plane logs, and you can do it with metrics if you are gathering metrics from the control plane, which I advise to do that because those are pretty important.
So are you talking about eBPF's ability to see these Kubernetes events? It raises the question, does Kubernetes, is it aware of eBPF at all? Is there any sort of synergy between the two? Or when you're writing eBPF, are you forced to kind of figure all that out yourself?
So when you write eBPF program, you need to solve the Kubernetes relationship by yourself. You're using Linux primitives like namespaces and C groups in order to actually get to the exact container, exact pod, exact deployment. And it's really interesting and challenging work, but it's a must if you want to translate the kernel layer into application layer. And the eBPF, I think what's great about it is it sees the data from the control plane as it was from an application, because at the kernel level, it's just an API. So when you translate it to Kubernetes layer, you can actually detect, oh, this API is from the kubelet. So it must be a lot more important than others. So you can do that, but you have to navigate through Kubernetes layers in order to find out which pod is responsible for this API.
You said kubelet, that's the utility, I guess, you use to interact with Kubernetes, or what was that phrase?
So kubelet is the process responsible for managing the node. So each node in the cluster has kubelet on it, which is responsible for scheduling containers, reporting the status from the deployments back to the control plane. That's the Kubernetes unit inside the node.
One more question, and then we'll just get into Groundcover itself, talking about that in detail. Prometheus and Grafana seem to play a role in observability. I don't think it's specific to Kubernetes, but can you just kind of say what those two are and maybe say what their role is relative to Groundcover also, if they are still used or not?
Yeah, so Prometheus is the time series. It's a lot of things, actually. It's a time series database. It's a format to transfer metrics between endpoints. And it's also a query language. So I think it's one of the biggest building blocks of time series databases, Prometheus. So it's also an open source, and also Grafana. So Grafana is an open source that built, I think, originally around metrics and specifically Prometheus. And it's a visualization tool. So you can visualize metrics fetched from Prometheus in Grafana and doing it with all the visualizations that we know, like trend lines and bar charts and pie charts and gauges, in order to make sense from all those metrics. Nowadays, Prometheus has competitors like Victoria Metrics, which I think It's the next generation time series database, but it still holds the same protocol and query language like Prometheus. So you can still use Prometheus query language to fetch from other time series database because they're all implementing the same protocol. So it's really common to see Prometheus deployments in Kubernetes because a lot of the metrics are stored there. And it's the first thing to do when you deploy a Kubernetes cluster and you don't exactly have a plan of how you want to monitor that.
So let's get more into Groundcover, and we can come back to Prometheus and Grafana and the relationship to Groundcover sort of daily usage. So at the beginning of the episode, you mentioned some of your motivation for starting Groundcover. Can you get a little more into the story of how it was started? How did you get your initial customers? What technology did you have at the beginning? Did you start with eBPF? Just kind of give us a sense of how things got ramped up.
So we started with a problem. It was right after the story I had. I spent with the team 2 or 3 months implementing all those metrics and all those traces and establishing dashboards. And, I was really proud of the team. It was really hard work and it worked really well. And then the CTO came and said that the vendor that we used, the usage, the observability cost was increased by 5 times. So he asked for us to remove all those metrics and all those traces. And for me, I felt like it was a failure for me as a chief architect that I could not understand the cost of observability. And at that time, I was trying to understand, is it me or is there something broken in the ecosystem? And from there, we Shachar and I are good friends and we sat together and he had similar experiences. So we felt like, okay, maybe we're onto something. And we talked to more and more VP R&Ds and chief architects, and we saw this as a common problem. So we saw there are 2 major problems. One is companies don't have enough information, and they're working really hard to get more and more information, spending time on that and not deploying new features to customers. And the second one is the companies that do have the information, they cannot pay the price for holding it. So they're actually reducing some of the information in specific environments, or, they do not deploy it on development environments, and then they miss bugs or anomalies in their dev and staging environments. And we realized we need to do something different or to solve it better. And we kind of walked with this idea for a few months, wondering how we can do that in a frictionless way. We realized we have to do observability in a frictionless way. So no friction for onboarding, no friction with payments. And then we encounter eBPF and we realize, okay, the first thing is we use eBPF. The onboarding is going to take 5 minutes. That's done. We get a lot of information, even more information we had in the past. But now we actually have a bigger problem. Now the amount of data is actually bigger. And we understood that you have to leverage stream processing. So you think about stream processing as pushing down some questions, common questions that you want to ask to the source of the information. So you don't need to ship all this data from A to B just in order to ask the question. You can just ask the question constantly when the data is originated and save a summary of it. So that way you can reduce the volume of data that you need to save and reduce cost with that. So once we realized those 2 can be solved, we started Groundcover, which is the first frictionless observability platform.
So I think one of the features of Groundcover is doing the processing in the nodes, maybe, instead of sending it back to a backend at your company. Is that different than how other observability tools work?
Exactly. So that's the first part, is the stream processing. So instead of sending all the data to somewhere else and then querying it, we're doing the processing at the node level and reducing the cost of sending it somewhere else, even in terms of egress, which means sending data outside of your cluster. That could be really, really disturbing to have this kind of, sending all those data. We're talking about terabytes a day. That's the volume that we're talking about in modern companies. It could be very, very expensive. But you touched on another point, which I think it's something fundamental with the observability word, is vendors trying to convince you to send as much data as they can. They charge by volume, so they want you to send as much data you can. And on the other hand, the customer, wants to save money. So they want to send as less possible. So you have this paradox between the vendor trying to send as much possible, the customer trying to, filter as much possible. And we realized modern observability vendors should be on the same page with the customer. So that's why we decided early on that we're not going to charge by volume. So it makes us on the same page. It's kind of alignment between us and the customer, that we do not encourage you to send data that you don't need. And we are on the same page with you, that you're going to have all the data you need and not data that you don't need. We're on the same page. And I think it's important to be aligned with your customers' needs.
When talking about eBPF, we said it has very tight time limits as to how much processing it can do. I'm guessing this stream processing cannot run inside of eBPF. So are we saying eBPF collects the data and then you have a different process running on each node that filters the data or monitors the data, I guess?
Yeah, that's correct. That's the trade-off between what to do inline inside the eBPF programs and, how much can we push the boundary of doing everything we can in the eBPF because it will be much more efficient, and how much we offload to do it out of bound and in other process that will take this information. And I think we are constantly trying to understand where are the boundaries for that. We are doing a lot inside eBPF to make sure we are sending only data we need in order to reduce the total computation cost. And the big important thing to remember is the expensive part is to send data from the node itself, because that will involve in serialization, deserialization, network between availability zones and so on. And that will be expensive. So as long as you can push down filters as low as you can to eBPF layer, and on top of that, do the out-of-bound stream processing in not interfering the application, I think that's the way to go. And that's the way to make it frictionless as possible in terms of affecting the application.
So if I'm using Groundcover, I could imagine three situations. One, I'm using stock eBPF programs from you, or you're installing them for me. Two is I'm using your eBPF monitoring, but I've configured it in some way. I've told it what to look for. And three, I don't know if this ever happens, but as a customer, I actually write my own eBPF. I'm just wondering in Groundcover, which of those is most common or which is possible?
The first and second options are pretty common. We see customers, trying to make it run. So we have this number 5 minutes in Groundcovers that it should be running under 5 minutes, no matter the cluster size. So we're doing everything we can to make it as fast as we can, no unnecessary questions, just works. But obviously, more advanced users can configure the eBPF programs and tracing. So if you don't want to capture, Redis protocol, for instance, some customers are not interested in that. Some customers are really interested in that. So it's opinionated. We will allow you to write filters in order to, drop some namespaces, some workloads, some protocols. That will be a more advanced usage of Groundcover. We still do not support ad hoc eBPF programs. And to be honest, I did not get any requests for that because I think most people don't really want to write eBPF programs. They just want that it works. But it could be an interesting idea to make it dynamically. So maybe add dynamically eBPF programs on demand. So definitely something to think about.
You mentioned the 5 minutes setup period, I guess, for trial. What's actually going on there? How is the eBPF program loaded on all of my nodes? If I have a lot of nodes running, what's distributing the actual program to those nodes?
So we it's not a trial because our first cluster is free forever. So what we do is we use daemon set primitive, which basically tells Kubernetes that you want to run this pod on each and every node. So we kind of ask Kubernetes to take the responsibility of managing it for us, because what we want is to have our own eBPF programs running on each node. So we use daemon set for the sensor, and from there, we guarantee that each and every node has this eBPF program running and loaded into the kernel.
You saying daemon set, is that a Kubernetes API or is that something?
Yeah, so that's a primitive from Kubernetes primitive that making sure that you get a copy of this application on each and every node. The usage for that will be monitoring solutions, security solutions, maybe infrastructure. So imagine you want a DNS server on each and every node, or you want a CNI plugin or any network related or storage related drivers on each and every node. It's like the daemons on our old operating systems.
Right, something that's always running. So maybe touching back to Prometheus and Grafana, what sort of dashboard and visualization features are inside of Groundcover, and in what cases do I still pipe the data to one of these open source platforms?
So we decided really early that we really love Grafana. We do not want to build custom dashboard. We focus around the eBPF and the databases behind it and the data model and the performance of that. And so we do not want to build another dashboarding system. So we made an architectural decision to use Prometheus as our query language from the beginning. So you can basically get your Grafana and route it to our platform and fetch all the data from our platform as it was your Prometheus. We also host Grafana as part of our solution. So in order to also eliminate that friction if you don't want to. So we also have all the common, visualizations as heat maps and trend lines and stacked bars and pie charts, all the regular thing. Because once we decided to use Prometheus as the query language, we could reuse a lot of components that already know how to work with that.
I think that makes a lot of sense. How about, this is a little behind the scenes, but you're using C or like a C-like language to write the eBPF. What other languages are used at Groundcover, say, to implement the stream processing? What languages do you use?
We are using Golang as our major programming language. We had a long discussion between Golang and Rust and decided to go with Golang because of the ecosystem. We also took a lot of inspiration from projects like Victoria Metrics, which took Golang to another level of performance and memory management. So we're taking a lot of concepts also from them. So Golang and C, and behind the scene, we're using Victoria Metrics as the database for metrics and ClickHouse for logs and traces and events. Both are amazing technologies, really inspiring piece of technology, and we're trying to squeeze it to the max for our use cases.
Can you say a bit more about Victoria Metrics? I hadn't run across that one.
Yeah, Victoria Metrics is an open source time series database. I think it's somewhere around like 5 years old. Definitely winning on every benchmark we did. And they have a lot of white papers and benchmark they did. It's like the next level for me of time series database. So they took Prometheus concept and brought it to a new era, a new level of implementation. So I'll definitely encourage everyone to check it out, especially if you're using Prometheus today or using Tanos. I think that will be probably pretty easy drop-in replacement and save you a lot of time and money.
Speaking of open source, how about Groundcover itself? I know the whole project is not open source, but there are maybe some open source components that you guys have been developing.
Yeah, we're trying to contribute to open source wherever we can. We released Moore, which is a CLI tool for Kubernetes CPU and memory monitoring. We also released Caretta, which is an eBPF sensor that demonstrates some of the abilities of what you can do with eBPF. So that could be also a good starting point for people or engineers who want to play with Kubernetes and eBPF specifically. It's a pretty cool project. You can get a lot of meaningful information from it, a lot of network metrics from it. So we are contributing to open source wherever we can. I think the world of software is pushed by open source, and we're trying to play our part wherever we can.
Going back to Go for a second, I think Kubernetes itself is written in Go. Is that true?
Yeah. The core of it, yeah. The kubelet itself, yeah.
How about this case study you had on your blog? You guys have a pretty extensive blog. I found it interesting to read through. There was a company or a project called Common Ground, and I know they used Go on AWS, but Python for machine learning on GCP, which is a split that I've seen myself, where you used both cloud providers. What observability challenges were there with this sort of dual cloud setup?
So I think whenever you have different deployments on different even regions or even products, for instance, Kubernetes and serverless. Or so even that will be really challenging to get a full picture of your production posture. So obviously having two cloud providers will be not an easy task to monitor. What I believe is that you probably want to have a monitoring cluster. So dedicated cluster for monitoring solutions, and then configure all the other clusters and all the other clouds to send data to this cluster. In that way, you guarantee that this cluster will remain available, even if you have some kind of disruption. And you also get a full picture agnostic to the cloud itself that is running. So you want to push all the data to one place. You probably want to use some kind of standard formats like Auto or Prometheus Remote Write or other open standards to consolidate the data. And then you need a strong backend, observability backend that will be also cost efficient in order to hold this data and retain it to the retention you need.
I had kind of forgot about serverless in this conversation. That does seem like it presents a challenge. So Kubernetes seems to mostly deal with long-running containers, but I imagine a specific system might have long-running containers, but also use serverless, maybe specifically Lambda. I guess in that case, you're going to observe it when it makes that call, or how do you even know that it's made a call to a function like that?
So when you're using eBPF sensors, you only need one side of the conversations instead of having the two sides when you're using traditional instrumentation. So as long as your lambdas at the end, talking to something orchestrated in Kubernetes, you're fine. But there are cases when the entire stack is lambda, for instance. And when you have this situation, you kind of need to instrument your application anyway. So specifically in Groundcover, that's why we have these endpoints that can allow you to ingest data from external sources. So if you're using any open standard, Zipkin or Jaeger or OpenTelemetry, of course, you can just ingest external data, and we make sure to treat it as a first-class citizen, the platform itself.
So I guess going back to that 5-minute setup process, what do I get at the end of those 5 minutes? What turns on? What do I start seeing? Is it the data flowing into my Grafana instance, or how do I know I've succeeded in the setup process?
After you deploy Groundcover, you'll go to the platform itself, the app.groundcover.com, and you immediately see all your workloads with all their golden signals monitored by the platform. So you don't need to do anything in order to do that. It will be automatically created with your account and your email or the registration API key. From there, you can explore. We have the, I think, pretty cool map view. So you can visualize all your production workload in a map. And that's pretty impressive to see, what you created in a map view, and you all of a sudden detect some kind of weird things that you never thought you'll see. You see that some third parties applications are actually reporting some things to some vendors, and it's really interesting to see. And of course, from there, you can also integrate with other third parties. So you can integrate with Autolink Gesture, you can integrate with your Grafana, you can integrate with our alerts and Slack, and to set up as your primary solution for observability.
Two things there, and then we'll start wrapping up. You mentioned golden signals. I have down here latency, traffic, errors, and saturation. I'm not sure what saturation means, but are those the signals, or does it just mean like whatever signals are important to you?
So I think golden signals is traditionally, yes, it's those signals. You have the equivalent of that. It's called the red signals. It's the same thing without the saturation, which is a bit more complex topic. But yeah, those are the signals, the golden signals, which according to a lot of SREs, those are the signals that you want to start monitor when you have no idea what is important to you.
So does saturation relate to CPU usage, or is it a networking thing?
So it could be. It depends on what resource your application is actually consuming. So saturation will tell you how much of the resources that you require are you maxing out. So if you're maxing out your resources, you're soon getting your limit. So if your limit is bounded by CPU or by network or by disk, that will affect your saturation rate.
And then one final clarification, you mentioned getting a map of your system, that's not an eBPF map. That's like a visual boxes and lines type of map. Or
yeah, sure. Map could be a word that is representing different stuff in this talk. But yeah, I'm talking about a visual map that will guide you where data is flowing inside your system and outside, honestly.
Great. Let's start wrapping up. I think when this episode airs, we'll be looking forward to 2024. So it might be a little bit far ahead, but what do you see as the future of eBPF in the industry and at Groundcover? What are you going to do in 2024 or looking forward to doing in the future?
I think eBPF will eventually be on each and every server that we use. So if you have a production platform that's running servers, you're probably going to run eBPF programs for a lot of tasks, because we're just started seeing what we can do with eBPF in terms of security, in terms of performance, in terms of observability. So eBPF is definitely the future, and we just started seeing it. And all the vendors in the security or observability domains are going to leverage it. And that's exciting for me, because we are constantly working on pushing eBPF boundaries as far as we can. So I think 2024, as we all know, is also going to be interesting in terms of AI and how do we make sense from observability data with AI. As you know, the volume of data is getting crazy. And with that, it's getting really hard to make sense of it. So there is this promise of AI getting us guided with that.
How can people learn more about Groundcover or follow you online?
So you can follow me on LinkedIn or Twitter. Also, we're writing a lot of blogs. All the engineering are really interested in writing blogs, technical blogs in Groundcover. So you can go to the website and go to blog. And feel free to send me a message regarding eBPF or observability.
Great. I'll put links to those in the show notes. Thanks for joining me today, Ches. This has been interesting.
Thanks for having me. It's really cool.
This has been Philip Winston for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.